All right, here are solutions for quiz 1 for Math 252. In this first problem, or first section, I suppose, you have 4 different limits that you're asked to evaluate, and on most of them you have several options in terms of what you do. These first two, what I had in mind is that these are section 2.5 questions. So I guess maybe I'll call it option 1 is to use section 2.5 methods. And to use section 2.5 methods, you stare at this thing and you try to factor the numerator and the denominator. So you might notice that there's an x in all terms in the numerator and likewise in the denominator. So I can say that that thing is equal to the limit as x approaches 0 from the positive side of x times x cubed plus 2x squared minus 5. And we'll divide that by x times 2x squared plus 4x. Wait a minute, you might say. Could I have factored out more? Couldn't I have factored out an x squared from the denominator? Yeah, in fact, you could have. You don't have to, but you could have. If you had factored out an x squared, you wouldn't have an x squared in the numerator to cancel it with. So I don't. I leave it kind of like this, but you can do whatever you want. That thing that you wrote up there is equal to the limit as x approaches 0 from the positive side. If you took the first 4 weeks of 252, you'd write lim equal here. I don't think that's necessary because you're writing limit. So this limit is equal to this limit. It's equal to x cubed plus 2x squared minus 5 divided by 2x squared plus 4x. It's equal to this thing. And it turns out that this is a limit that you can evaluate. The way you can evaluate this limit is by kind of thinking about what would happen if you plugged in a value very, very close to 0 into the numerator and the denominator. Well, what would happen, and this I'm going to write in red because this is kind of informal here, is this term would get close to 0, this term would get close to 0, and this term would remain negative 5. And in the denominator, I would get something that's really, really close to 0, but positive. In other words, I would get a positive small number. That's a strange thing to write, hence the reason why it's in red. You could cut that step out altogether and just come to this conclusion that I'm going to write in blue, which is that when you take a number and divide it by a really, really small number, it gets big. And all you got to do is worry about the sign. I got a negative divided by a positive, so I would say this is negative big. In other words, my conclusion would be that this limit is equal to negative infinity. There's other ways you could do this problem. Maybe I won't go through and do every problem multiple ways, but I'll just comment here that option 2, you could also use L'Hopital's rule. I didn't have that in mind when I wrote this problem, but it is an indeterminate form. Right, the top as it's written now gets close to 0, the bottom gets close to 0 as you evaluate the limit when x gets close to 0. So you could apply L'Hopital's rule, and that'll work out perfectly fine as well. But since I had these methods in mind when I wrote this problem, I'm just going to detail this one. I'll have plenty of chances to use L'Hopital's further down. So maybe I'll call that good. Second problem. Again, you could use L'Hopital's rule. And the reason why is this is an indeterminate form. The top gets really, really big when you plug in a negative large number, and the bottom gets really, really big when you plug in a negative large number. And maybe those bigs are negative or positive, but really it doesn't matter. Either way, you get an indeterminate form. So option 2 is you could use L'Hopital's again. It turns out that if you use L'Hopital's rule here, you're going to have to use it a whole bunch. I think you have to use it 4 or 5 times by the time you narrow these exponents all the way down. But you will get your answer if you use it enough times. But that, again, is not what I had in mind. What I had in mind was to, again, employ 2.5 methods. And in 2.5, we learned that when you're looking at a rational expression like this and asked to evaluate the limit as x approaches infinity or negative infinity, all you got to do is look for the winner. The winner is the term of largest degree, which in this case is this term right here. X to the 5th, the 5 is larger than any other exponent. So this guy wins out. Yeah, the top gets big and the bottom gets big, but this gets biggest. This stuff is big. This is even bigger. What essentially ends up happening is I get some number up top divided by negative infinity. And yeah, that number up top is really, really large, but it's not nearly as large as what we get from this term right here. So because this guy is the winner, I get something divided by negative big, and something divided by negative big is small. And yeah, you could argue negative small, but it's negative 0, and negative 0 is the same as positive 0. So our answer is just 0. I'm going to write what I just said a little bit more formally because it seems like the right thing to do. I'm going to say that this is equal to the limit as x approaches negative infinity. And the way we showed that you could show your working class is I could factor out an x to the fourth from the top and the bottom. I could say that the top is really 2 plus 1 over x minus 7 over x cubed plus 2 over x to the fourth. And this is what would result if I factored out an x to the fourth from each of those terms. And in the denominator, if I factored out an x to the fourth from each of the terms, I would have 2 over x minus 3x. And this is a limit you can evaluate. I'm going to write this in red. As x gets really, really large, negative, 2 stays at 2. 1 divided by something huge is something really small, in other words, 0. Same idea here, 0. Same idea here, 0. And then we're going to divide that by, this is 0. And negative 3x. When I plug negative infinity into this, I'll get minus negative big, in other words, plus big. So what I end up with is 2 over big, and as we saw, 2 over big is equal to 0. If you don't want to write this, I guess you could use limit laws to rewrite this a couple different times and eventually come to the same conclusion. I'm going to go ahead and leave it like that for the sake of the length of this video, because I feel like this is already getting kind of long and I'm only done with 2 of the many problems. Part C. Here's one where I had L'Hopital's rule in mind. The reason why is this e to the x thing right here. There's no factoring that we can do. There's no easy way to evaluate this thing, I don't think, using 2.5 methods. So instead we're going to use L'Hopital's rule. The first thing we're going to notice is that as x gets close to 0, e to the 0 power is 1. 6 times 1 is 6. 6 minus 6 is 0. Minus 0 minus 0. Divided by, if this x is 0, 0 cubed is 0 times 2 is 0. This thing right here is the 0 over 0. I'll put quotation marks around that form. This is 0 over 0 indeterminate form. I don't know that I need you to write that, but it's true. It's the 0 over 0 indeterminate form, and that's what allows you to apply L'Hopital's rule. So with L'Hopital's rule, maybe an equals with an h on top. Again, that's optional. You don't have to say that. You can say that this is equal to the limit as x approaches 0 from the negative side of, and then take the derivative of the numerator and the denominator. The derivative of the numerator would be 6e to the x minus 0 minus 6 minus 6x. The derivative of the denominator would be 6x squared. You get those derivatives, and it turns out that we still have an indeterminate form. Try plugging in 0 all over the place here. This is still 6. Minus 6 is still 0. Minus 0, we're still 0. This is 0. Not only is this a 0 over 0 indeterminate form, so is this guy. So therefore, I can apply L'Hopital's rule again. And L'Hopital's rule tells me that that limit is equal to the limit as x approaches 0 from the negative side of the derivative of this divided by the derivative of this. The derivative of this, 6e to the x minus 0 minus 6. The derivative of the bottom is 12x. Yeah, I was feeling kind of funny to make you keep doing this over and over again, because this is still an indeterminate form. Try plugging in a number slightly less than 0. This gets really close to 6. 6 minus 6 gets really close to 0. 12 times 0 is really close to 0. In fact, this third one is still a 0 over 0 indeterminate form. Do it again. This equals, according to L'Hopital's rule, the derivative of the top, 6e to the x, divided by the derivative of the bottom, which is 12. I can evaluate this limit. There's a limit. Oh, I shouldn't just say it equals that. I should say it equals the limit as x approaches 0 of that. Shouldn't be lazy here. And this is a limit that I can't evaluate. When x gets really, really close to 0, e to the 0 power is 1. 6 times 1 is 6. And 6 divided by 12 is 1/2, which is the answer to this original limit here. And that's the answer to part C. And really what I did is I applied L'Hopital's rule 3 different times because I had these 0 over 0 indeterminate forms 3 different times. That gets me here. All right, and then this last problem, part D here, very challenging problem, although you had seen it before, or at least you saw something quite similar to this. And I think I told you in lecture that I'd give you the same problem if you wanted it, and I think you guys decided that you did want it. So let's go through the steps. You're figuring out the limit as x approaches positive infinity of the natural log of x divided by x plus 1 divided by e to the negative x. And what you can do is first determine that this is an indeterminate form, that x divided by x plus 1 as x approaches infinity gets really close to 1, and that the natural log of 1 gets really, really close to 0. and that e to the negative infinity gets really, really close to 0. So I have an indeterminate form, the same type 0 over 0, so I can apply L'Hopital's rule. You have some options. You can apply L'Hopital's rule immediately, or you can apply some log rules. Right? Because when you apply L'Hopital's rule, you're going to be taking the derivative of the numerator and of the denominator. The derivative of the numerator is going to be tough. I mean, not that tough. You might be able to do it, but it would be easier to find the derivative if you rewrite it like this. So note that this is not using L'Hopital's rule. I'm not using L'Hopital's rule here at all. I'm just rewriting this using log rules because this form of this will be easier to take the derivative of. Again, you don't have to do it this way, but you can if you want. So either you use L'Hopital's rule here, because you notice that this original thing was this 0 over 0 indeterminate form, and you say that this is equal to the limit as x approaches 0 infinity of the derivative of the top, which is 1 over x minus 1 over x plus 1, divided by negative e to the negative x if I take the derivative of the denominator. It's one way you could do it, or you could say that this thing right here equals, using L'Hopital's rule, the derivative of the top would be 1 over all that stuff times the derivative of that stuff. I'm using the chain rule here. And so to figure out the derivative of this stuff, to figure out the derivative of x divided by x plus 1, you got to use the quotient rule. And the quotient rule tells me the derivative of x divided by x plus 1 is the derivative of f, well, which is 1, times the bottom, g here, which is x plus 1, minus the derivative of the bottom, which is 1, times the top, which is just x. And that whole thing gets divided by the bottom, which is x plus 1, squared. So you have the freedom whether you want to get to this stage or to this stage, although really I think these two stages are equal, because this here is x plus 1 over x times 1 over x plus 1 squared. And this equals, I can cancel out this x plus 1 and this plus x plus 1 and get that it's 1 over x times x plus 1. So that's what the top would look like. And then I guess the bottom in each of these cases is e to the negative x. That doesn't look good. No, sorry, negative e to the negative x if I take the derivative. However, what I wrote here in red is the exact same as what I have here in blue, because if you get a common denominator here, you would multiply this by x plus 1 over x plus 1 and this by x over x, so you would have x plus 1 over this common denominator minus x over this common denominator. That whole thing is over negative e to the negative x. So really what you would have is, if you subtract the numerators, you got 1 over x times x plus 1 divided by negative e to the negative x, and it's the limit as x approaches infinity of this expression right here. And unfortunately, I believe this thing is still an indeterminate form. Let's see if that's the case. Maybe I can clean it up a little bit. Well, I could say this negative exponent, I could write it up on the top of the fraction. I could say this is negative e to the positive x power, and I should probably include my limit. So let's say it's the limit as x approaches infinity of the negative of e to the x power divided by x times x plus 1, because I have 1 over this stuff, so really this is down on the bottom, and then I can move this up to the top by getting rid of the negative exponent. I have this thing right here. Question, is this indeterminate? Yep, it is. It's not this type of indeterminate form, it's actually the infinity over infinity type of indeterminate. Because e to the infinity power is really big, and infinity times infinity plus 1 is really big, so it's this type. And what that means is I can use L'Hopital's rule again. So I get that this is equal to, according to L'Hopital's rule, the limit as x approaches infinity of the derivative of the top, which is negative e to the x, divided by the derivative of the bottom. Well, I could view the bottom as x squared plus x, and then maybe I could see that the derivative of the bottom is 2x plus 1. Distribute this x through x squared plus x, take the derivative of that, you get 2x plus 1. That leaves you here. Unfortunately, you still have a infinity over infinity indeterminate form. All right, just like I did here, I also do there. Because e to big is still big, and 2 times big plus 1 is still big. So what that means is I can use L'Hopital's rule again. And I got the limit as x approaches infinity of the derivative of the top is negative e to the x. The derivative of the bottom is just 2. Aha! We can figure this out. All right, the limit as x approaches infinity of this thing right here is negative infinity. And the reason that's true is e to the infinity, e to the big is big, and negative of that is negative big. Divided by 2 is still negative big. My answer to this entire mess ends up being negative infinity. Wow. One more little arrow maybe I'll write just to kind of connect all my work is that had you gone down on this red path at this point, you'd jump back up to here. Note that this is the exact same as this. Oh my god. This thing continues, huh? All right, we've got a whole other page here. Anti-derivatives. We're dealing with anti-derivatives. We're given a function and asked to find its antiderivative. The trick to this one, or a trick, is to rewrite the function. Really, this is saying that f of x is equal to 1/3 of this whole mess, x cubed plus x to the 1/3 power, which is how I'm going to rewrite this guy, plus 3x to the negative third power, which is how I'm going to rewrite this guy, plus 1/3 x to the negative 1 power. Yeah, let's leave it like that. Plus 3. And yeah, I thought I was funny putting all these 3's in here. Now I realize that I was not, but what are you going to do? So you got this guy here, and you're asked to take the antiderivative of it. Well, the good news is that this constant right here doesn't matter at all. Constant times a function, I can just leave that constant alone. Really, most of my work is going to happen in here. The derivative of x cubed, well, if I raise 1 to that exponent, I get x to the 4th power. But if I were to take the derivative of x to the 4th power, I'd get 4x cubed, not x cubed. So I better throw a 1/4 out here to make everything work out nicely. Similarly, the exponent on x to the 1/3 will become x to the 4/3 if I add 1 to it. However, I don't want there to be a coefficient, so I better put a 3/4 right here. 3x to the negative 3rd power. Well, I guess I could put a plus, but it's going to end up being negative, so I'm going to go ahead and throw the negative down here. The exponent will become x to the negative 2 power. But if I was taking the derivative, I'd take this negative 2 down in front, and the negatives would cancel and give me a positive. That's good, but I want it to end up being a 3. So I guess I should throw a 3/2 here. And now note when you take the derivative, the negative 2 comes down, the negatives cancel, the 2's cancels, and I'm left with 3x to the negative 3rd power. This guy, a little bit of a trick. Because you're like, oh, power rule, I've done so much power rule, I'm thinking power rule, it must be power rule, it's not power rule. The derivative of the derivative of natural log of x is x to the negative 1 power. The antiderivative of x to the negative 1 power, aka 1 over x, is the natural log of the absolute value of x. So inside the parentheses, this is what I get. And you're not done, because we have to deal with this 3 right here. Its antiderivative would be 3x. And you're still not done, because you should throw that constant out there at the end. Something like this is perfectly fine. You can leave your answer like that. If you're one that feels like rewriting things, hey, you go right ahead. You could call this 1/12 x to the 4th power. Feel like it, you take this 1/3 times this 1/4. You could take this 1/3 and distribute it here to get 1/4 x to the 4/3 power. Take this 1/3 and distribute it through and get 1/2 x to the negative 2 power. If you don't want to leave negative exponents, you could say 1 over x squared. It's kind of a matter of preference. And this 1/3 times this 1/3 would give you 1/9 times the natural log of the absolute value of x. And then plus 3x. Do I have any other x's to combine that like term with? It doesn't look like I do, so I'll leave it alone. Plus c. Either of these, totally good. And work as your answer. So we'll call that good. We got one problem left. In this one, I'm told that the second derivative for some function g is this mess. Find that function. Oh, and by the way, g of 0 equals 3 and g of 1 equals 10. These two statements will allow me to not have any plus c type things in my answer. And let me show you how. Let's first figure out g prime of x. Well, g prime of x is just the antiderivative of this guy. So kind of like I was doing above, I would end up with something like this. The derivative of 8x cubed, bring the 3 down, that gives you 24. Subtract 1 from the exponent. Yeah, 24x squared, that checks out. The derivative of x squared is 2x. Yeah, that checks out. The derivative of 10x is 10. Nice. And don't forget to put in this plus c. But I'm not done there, because I really want to figure out g of x. Well, g of x is just the antiderivative of the derivative of g. So I got to figure out the antiderivative of this mess. I can do that. Be 2x to the fourth plus 1/3 x cubed plus, 5x squared plus cx plus d. Where'd that all come from? Well, I guess using the power rule in reverse, I'd add 1 to the exponent, that would make it a 4. But when I take that exponent, take the derivative of it, I want to end up with 8 as coefficient, so there better be a 2 here. By that same logic, this term is 1/3 x cubed, this is 5x squared, this is cx, the antiderivative of this c, and then I must have the plus d. But I don't need a c and a d to represent these two different constants because I have these two statements. Because g of 0 equals 3, I know that when I change all the x's into zeros, 3 must come out. 3 must be equal to 2 times 0 to the 4th power, which is 0, plus 1/3 times 0 cubed, which is 0, plus 5 times 0 squared, which is 0, plus c times 0, which is 0, plus d. In other words, d is equal to 3. Cool, but what about c? Well, I can figure out c. Maybe I need to switch color here. From this statement, I know that when I put 1 into this function, 10 must come out. So 10 must be equal to, let's see, if I put in 1 here, I get 2 times 1 to the 4th power, aka 2, plus 1/3 times 1 cubed, which is 1/3, plus 5 times 1 squared, which is 5, plus, remember, d is 3, so I get 1c here, plus 3 in place of d. I get this mess right here. If you solve this, things work out nicely because 2 plus 5 plus 3 is 10. So if you subtract 10 from both sides of the equation, you get 0 is 1/3 plus c. So therefore, c equals negative 1/3. And now that you know what d and c are, you can come back up here and say final answer. I got g of x is 2x to the 4th power plus 1/3 x cubed plus 5x squared plus, and then instead of writing cx, I'll write minus 1/3 x. And then instead of writing d, I'll write plus 3. And call this mess right here my answer. I think that finally ends this quiz, so I'll stop the video here.